Hey everyone, it's Mr. Canfield. Today we are going to be looking at something called definite integrals. So before we've looked at indefinite integrals, and today we're looking at definite. So it's a little bit out of sequence in the book, but I think it makes a little bit more sense with the way that we're learning. So I want to remind you of a couple of things that we've talked about. The first one is the Riemann sum. So we've looked pretty extensively at the Riemann sum given the parabola y is equal to x squared plus 1, and we found it with 4 rectangles. So when we found it with 4 rectangles, we got an approximation. I think we did from 0 to 4. And we got an approximation, and we were missing some space underneath. So an obvious way to reduce the amount of space that's there is to use more rectangles. And so what people did was they were like, you know what, instead of using 4, like, what if I use like 5 rectangles? And if we use 5 rectangles, there's going to be less space there. Like, instead of 5, what if I used like 100 rectangles? And so they go in, and this will take a little bit of time, but no, just kidding. So, but if we did 100 rectangles, those little spaces there, they'd be so much smaller. Be so much less space here. Now, you know what? Instead of doing 100, let's do 1,000, or let's do 1,000,000. You know what? Let's do infinity rectangles. And you might be thinking, can't do infinity rectangles because 100's too many to begin with. And sure, but what the idea here is that we took the limit as the number of rectangles approached infinity. So it was like the limit as the rectangles approached infinity. This isn't like official notation, I'm just talking about it. So it turns out that if we were to, and this is all provable, and in some classes they'll prove it, but we're trying to go toward the AP exam and you don't need this proof. In reality, the infinite rectangles that this adds up to is called the definite integral. So if we want the area underneath this curve from 0 to 4, we take what's called the definite integral from 0 to 4. And so we put these bounds on here. So the cool thing is we have basically everything we need to be able to do this already, because we know how to integrate x squared plus 1, right? We add 1 to the exponent, divide by our new exponent. So I like to put the 1/3 out front sometimes. Sometimes you can do it any way you want. And then here, this is a plain 1, and so we took the derivative of x to get 1, so it's going to be plus x, and we would do plus c. But now that we're dealing with these 0 to 4, we got to talk about how to deal with those. And so what we do is we actually can say 0 to 4 like this. And what this is saying is, hey, we're going to actually plug in 4 here, and we're also going to plug in 0. And we're just going to wind up subtracting them. So here's what I mean. If I go in here, 1/3, I plug in 4 plus c minus, so I plugged in 4, right? Minus, we're going to plug in 0. You might notice something. I have plus c here, and I have minus plus c. What's going to happen to those c's? Well, I'm getting a little bit ahead of myself. Let's see. So 1/3, 4 to the 3rd. Let's see. 4 to the 3rd is 4 times 4 is 16 times 4 more is 48. So 48 over 3. Oh, I think that actually goes in. Plus 4 plus c minus minus c. Right? Those are zeros. Hey, what's c minus c? Guess what? The c's always cancel out. So we actually get to go up here and we get to say, hey, you know what, instead of saying plus c, we're just going to go, maybe not even put it there, because when we're dealing with definite integrals, the c's always cancel, you don't need them. If you forget and you write them, still works. Let's see, 48 divided by 3, I think it's 16. Oh, wait, no, I messed up, because I did 16 times 3, not 16 times 4, that's 64. 64 over 3, okay. So, my bad, sorry. 64 over 3, I don't think that, because 6 and 4 add to 10, That's a secret for dividing by 3. You add the digits together, and if you can divide the digits by 3, then you can divide the whole thing. So I get 10 here. They don't divide. So 64 over 3 plus 4. So if I really want, I could turn 4 into thirds by saying times 3 over 3, right, and get 12 thirds, and say 78 thirds. And if I remember correctly, that was the exact area that we got in the Riemann sums video. But this right here is a way for us to get the exact area underneath a curve. And so the integral, and so here, let's look at we'll just look at the notation really quick. The way that this works, the integral of f of x, I'm using like the lowercase f of x. So like, it'll be in cursive a lot of the time, but f of x dx from a to b, we say the integral of that is equal to, so for derivatives we write f prime. For integrals, we'll change a lowercase to an uppercase, and we'll say f of x evaluated from a to b, also known as f of b minus f of a. So capital F's, that's our way of kind of showing through notation that if I take the derivative of this, I get that. So this is kind of the lead up to it. I know I deviated from Stu's notes on this. He does a great job. He always does a great job talking about things. So I don't want you to think that this is worthless. I'm not going to talk through that the way that he does. I think it's great. And I think it's great that you have multiple ways to think about things. I just want to give you a different way to think about it. You have more resources. All right. So the one thing I have not talked about at all with this area stuff, integrals, definite integrals, we got a positive number here. They can be negative. So like if I have a curve that goes underneath, so we would talk about this area as being a positive number, but when we would calculate it, the integral actually winds up being a negative number. So it winds up being a very descriptive and helpful number. So we're just going to go through and do a bunch of his examples. So it's neat. He starts out just with a picture here that lets us really, really think about what's happening. So it says, below you are given the graph of f of x formed by lines and a semicircle. So we're guaranteed this is a semicircle. If they didn't tell us this in the problem, we wouldn't be able to really know anything about its area. Let's see. So, and these are all line segments. So we can assume they're perfectly straight. Any slopes that we can count out are accurate. It says find the value of the definite integrals. And the first one says, oh yeah. The first one says, what's the integral from 4 to 4 of f of t? Well, if we just think with me for a minute, we're not even going to use the graph for this one. So remember we said this is going to be written as f of 4 minus f of 4, big F of 4 minus big F of 4. But no matter what this is and no matter what this is, wait a minute, they're the same thing. What is something minus itself every time? And so this is a true thing for all integrals ever. If the top and bottom bound, so this is at 100 to 100 of f of x dx, it's 0. Doesn't matter. Oh, I should have put a dt there. It doesn't matter what those two numbers are. If they're the same, then it's 0. So it's a fun, you could have something really, really nasty looking. Like you could have, let's say 2 to 2 of like sine of x squared minus the natural log of e to the natural log of the square root of sine of x, then all of this to the 3/4 power minus 2 dx. It's like, something stupid like this, but since the bounds are the same, oh, it's 0. Cool, 0 work to do. All right, let's see, B. 0 to 1 f of t dt. All I have to do, so remember that the integral is actually the area. It's the actual area underneath the curve. So if I'm careful here, just trying to draw a slightly bigger version. I'm going to make sure I use his numbers and get everything correct when I do it, but just so we can talk about it. So here's 0, here's 1. You know what? Give me a second. Yeah, you didn't need to listen to me draw the whole diagram. Okay, so B says the integral from 0 to 1 f of t dt. So it's literally saying, hey, what's the area from 0 to 1 of f of t? Well, we're able to take something like this and just break it up into all of its little mini areas. So like the area here, let me just make sure I'm getting it right. Yeah, so it's a rectangle, right? Its base is 1, its height is 2. So what I like to do is kind of, as I'm breaking these things off, I'll actually, on the diagram, I'll write, so 1 times 2 is just 2, because I'll probably need this later. So I can just write that. Let's look at C, because that's literally the area from the x-axis to the curve. Now it says, what's the area from 1 to 3? F of t. Let's see. dt. So the area from 1 to 3. Oh, well, that's a triangle, right? And we know the area of a triangle is 1/2 base times height. Well, it looks like the base here is 2, and the height is 2. So 1/2 times 2 times 2. So we know that 1/2 times 2 is 1, and then times 2 we get 2. So this is 2. So then we get to D. Let me try to write them on the same side that he's got them. D says, so what's the area from 0 to 3 of f of t dt? So I literally can take these two areas from 0 to 1 and from 1 to 3 and add them together and get 4. 2 plus 2 is 4. And this is actually a chance for us to look at a property of integrals, and that is in definite integrals. We're capable of saying, hey, maybe I don't know this whole thing, but I do know the integral from 0 to 1. So if I find that, and then I add it to the one from 1 to 3, what we're able to say here is we're able to say that from 0 to 1 and then from 1 to 3, if I add these together, I actually get from 0 to 3. You know, if we think about this from a number line perspective, we're going from 0 to 1 and then from 1 to 3. So it fills up that whole piece of the number line. So it's kind of a neat thing that we're allowed to say. And at least for me, it's always kind of made sense from like I guess an intuition standpoint, like, oh yeah, we're going 0 to 1 and then we're picking up at 1 and going to 3. Let's see, E says, all right, this will need to be my last line, and then I'll have to figure something out. E says the integral from 3 to 6. Okay, 3 to 6. Okay. So some people like to break this up into two separate triangles. I am going to break this up into not two separate triangles, and just do one triangle. So for me, I see that it goes from 3 to 6. So that's 1, 2, 3. So it's a base of 3, and it's a height of 1. Or height of -1, because it's underneath the x-axis. So I could say the area of this triangle right here is 1/2 times 3 times -1, which is -3/2, or -1.5 if you want to do that. So, oops, I didn't finish writing this. Whatever. F of t dt. So I got -3/2. Then we get to F, and F is our next property of integrals that we need to understand. 6 to 3 f of t dt. So how are we supposed to reverse this? And so if you remember that the idea here is that from 3 to 6, it equals, and we don't know what big F is, but we know that it's big F of 6 minus big F of 3. If I take big F of 6 minus big F of 3 and I get that What would happen if I do big F of 3 minus big F of 6? You know, if you're not sure, just pick a random number. Like, let's just do this with a random number. So let's do 4 minus 7. What do you get with 4 minus 7? You get negative 3. What happens if you reverse that? You get 3. You get the opposite. So in reality, if we have the bounds reversed, it's just the opposite answer. So this is equal to, a lot of times what we'll do this is we'll say this is equal to negative from 3 to 6 f of t dt. So we'll get positive 3 over 2 for this one. All right. Shoot, lost track. Paused the video for 2 seconds and I got lost. Oh wait, just finished F. Okay. G. So G says, oh, okay. G just says take the integral from 0. All right, it's. I think it's a little bit of tedium at this point. I'm gonna kind of, you know what? I'm gonna go through it, and if you want to follow along, you can follow along. If you want to, you know, fast forward or skip ahead, go for it. Okay. So let's see. I would definitely try these, but I'm saying like it. Oh, I just want to find the area from 0 to 6. Okay, I'm gonna write bad notation. 2 plus 2 plus negative 3 halves. That's literally it. You just add them all up. So 2 plus 2 plus negative 3 halves. Remember, this is negative 1.5. It's easier for me to think about. So I got 4 minus 1.5, which is 2.5. So 2.5 or 5 halves. There, I look smarter writing 5 halves, but it's the same. All right. And then H says from 6 to 10. So do from 6 to 10. Well, if we're dealing with a semicircle, well, don't we know that the area of a circle is pi r squared? This is a formula that you are assumed to know on the AP exam. So what would a semicircle be? It would be half of that. So you know, if we take our A and cut it in half, there, it's cut in half now, right? It's missing the other half. I'm so funny. All right, now, so the area of our semicircle then is going to be 1/2 pi r squared, or pi r squared over 2. You know, whatever flavor that you like. So my radius of this, well, if it goes from 6 to 10, and it's a semicircle, and that's guaranteed to be a diameter, so then the radius is going to be from 6 to 8 or 8 to 10. The radius is going to be 2. So I can say it's 1/2 pi 2 squared, which is just 1/2 times pi times 4. And so we'll divide that by, you know, our half times 4, we get 2. So 2 pi. So the area of this part is 2 pi. So then if I want the area from, oh, well, so 2 pi, okay. All right, I says, oh, I's so difficult. It says go from 10 to 6. So remember, it's the reverse, right? So anytime we reverse, we just take the opposite answer. So it was 2 pi, now it's negative 2 pi. All right, J. Let's see. There we go. Okay, what does J say? J, from 0 to 10. Oh, super hard, from 0 to 10. It says take the integral from 0 to 10 of f of t dt. Literally, just add all these up. 2 plus 2 minus 1.5 plus 2 pi equals I don't care. It's a number. Let's see. Oh, wait. Oh, wait, yeah, that's J. Oh, then K is so difficult, right? It says from 10 to 0 f of t. Well, so whatever I got in the previous question, it's the opposite of that. So it's negative I don't care. What is this, 4? So 2.5 plus 2 pi, and then it would be the opposite. So, okay, fine. 2.5 plus 2 pi. That's what would be that answer. Then this one would be negative 2.5 minus 2 pi, right? It would be the exact opposite of it. Let's see. L says, let's see, L says take the integral from -1 to 0. All right, this one gets a little bit more challenging because I'm supposed to figure out it's like a trapezoid here. That's kind of tricky. All right, well, if I go to the actual function in the picture, just to make sure I get it really good. So we've got 4 and we've got 2. So our two different bases are 4 and 2, and our height here is 1. So I can do 1/2 base 1 plus base 2 times height. So that's 6. 1/2 of 6 is 3. So this is, this part's 3 right here. And I have a feeling he's going to go in and make me kind of get the rest of these slivers, which is, it's a little annoying, isn't it? Okay, he never puts a bound of -2 on there. So, all right. So I got 3 for L. M says, now let's go from -3 to 0 and get this whole shape. So for me, what I do for this is I would break this up into this triangle right here. Let's see, its height is 6. So it's 1/2 times 6, and then its base is 1. So 3. So we have 3 here. We have, wait, oh, that's the y value too. Okay. So we have 3 here. Let's find this whole trapezoid here. Instead of finding just like the little slivers, well, I guess I can find this sliver now. It's 6 and it's 4. So that's 1/2 times 6 plus 4. And then its height is also 1. So that's 10, so it's 5 when we divide it by 2. So this whole trapezoid here is 8. But it says one stick is 5, the other one's 3. And then this one here was 3. So if I'm asked to find the area from -3 to 0, I just add those up. 3 plus 5 plus 3, and I get 11. Then if I get 0 to -3, oh wow, it's the reverse, so it's the opposite. Why do you think he's having you do this every single time? Is it because he thinks you forgot? No, it's because he wants you to make sure that you're remembering this in the future. Now this one says -4 to -3. Oh, so this little triangle down here. Boo boo. All right, let's see. Well, it's got a height of 1 and it's got a base of 1. Base height. So its area is going to be 1/2 base times height. 1/2 times 1 times 1. Oh, but it's negative since it's down there. So this is going to be -0.5 or -1/2. Now we want to go from -4 to 0. So I'll just add those up, right? I'll get 11 plus -1/2, 10.5. Here's the real one. It says, go from -4 all the way to 10. Woo! So that's going to be the whole thing. Whoa, it's the whole thing. But if you remember, a few minutes ago, we actually already added these up. We did the 0 to 10. So I could do the -4 to 0, which we got 10.5. And then we could do the 0 to 10, which was this I don't care, or 2.5 plus 2 pi. So we could say this is 10.5 plus 2.5 plus 2 pi. So that's 12, 13 with the 0.5, so 13 plus 2 pi. And that's how I would write it. I wouldn't go find the decimal for the 2 pi. Ooh. Now it says take the absolute value of that answer. See how the absolute value bars are on the outside of everything? That stays the same then, 13 plus 2 pi. But then it says, hey, what about the integral of the absolute value of our function? So this is where it's a little different. And so what we need to do here is we need to say, anytime I had a negative area, which I realize negative area is not a real thing, but I had a negative integral. So that was -0.5, and this was -1.5. Now we have to treat them as if they were positive. So here, I'm going to take my 0.5, I'm going to add it to, what was all that? 11. Then we're going to add our 2 and our 2. Now instead of being, we're going to take the absolute value of that negative 3/2 and get positive 1.5, then plus our 2 pi. So that's going to be 3, 5, 6, 7, 18. It's going to be 18 plus 2 pi. So when you see that absolute value, that's telling you, hey, take this original graph and just anywhere we had negatives, make them positive. And lastly, this one's going from 1 to -1. So we're going to dress this up a little bit first. One's got a 2 there. Uh-oh. But if you remember our properties of integrals, it's actually pretty straightforward. So it says, go from 1 to -1 of -2 f of t dt. So what we're able to do is, well, first I can reverse the bounds, right? And say, we always want to go from least to greatest and throw a negative out front when we switch the bounds. Wait, but then it says negative and negative. I can actually pull that -2 out front. So a negative -2 is positive 2. So it just says, hey, go from -1 to 1, find the area underneath, multiply by 2. Literally it. So I think we've already got most of that. Let's see, that's, so from -1 to 0 it was 3, and then from 0 to 1 it was 2, so 3 plus 2 is 5. So 2 times 5, so 10, and we're done. All right. So here we're really looking at integrals as area. And you know, that's like how we were able to do derivatives and how they also tied into slope and how they really were the same thing. The integrals have the same connection that they draw, that they have, what did I say? Integrals have the same connection, same sort of connection, just with a different group of characteristics. There's the word. All right, so how much more do we have in this section? Okay, cool. So, oh, I love these problems because they look so bad and they're just, there's not as much work to do as regular integrals. So I definitely gave a little bit of a spoiler talking about the area the way that I did, but don't worry about it. Okay. So, so it says, suppose the integral from -2 to 5 of f of x dx is equal to 18. And then same integral of g of x is 5, dx is 5. And then from -2 to 5, h of x dx is equal to -11. And then if we go from -2 to 8, f of x dx, that's 0. So if we have that given, the first one says, hey, what's the integral from -2 to 5 of f of x plus g of x? You don't need me to tell you this. I think you can figure it out. It's just the two different integrals added together, right? From -2 to 5, so it's 18 plus 5. I got 23. Wow, that's hard. Well, then it says f of x minus g of x minus h of x with the bounds that we got. Whoa, believe it or not, it's just take 18, take away 5, then take away -11. Whoa. So I got 29 minus 5, I got 24. Whoa. Oh, but now we're getting fancy. So C says have 4 g of x. So I'm going to actually pull the 4 out front. Oh, and the bounds are not in the right order. So let me reverse the bounds too. Go from -2 to 5. Throw the negative out front. Oh man, he almost got me good. He almost caught me. No, he didn't. That was so simple. I'm so mean. All right. That's a 5. So like this thing right here is 5 times -4. So I got -20. All right, D. Oh yeah, these. Oh, I love and hate these. So this says -2 to 5 g of x plus 2 dx. All right. So here is where they start to get a little fancy. I'm gonna write an error that a lot of people make on this. A lot of people will say, "Oh, I know -2 to 5 is 5, so it's gonna be 5 plus 2, so it's just 7." Nope, he's not that. Because what was really happening before is we were taking an integral plus another integral. So what's really happening here is we're taking the integral from -2 to 5 g of x dx plus the integral from -2 to 5 2 dx. And so what's actually happening here is, well, yeah, this integral right here is 5. But this integral is something we have to go and evaluate. So if you remember earlier, the way that we did this was we would integrate it, like we would take the integral like we normally do. So this is going to be 2x plus c, except we're gonna leave the plus c off since we're gonna do the definite integral. We're gonna go from -2 to 5. And now all we do is we plug in the 5 and plug in the -2. And we get 10 minus -4, so plus 4. So this is 14. So 5 plus 14, and so our answer is actually 19. So and that's what the next two actually look like. Let's see. Okay, we're getting on in time. We're just, it's okay. It's okay, Canfield. It's going to be okay. All right. I'm trying to make these videos not quite as long as I know I can really drag on, and I want to make it something that is digestible. So the next one says take f of x minus 6. So in this one, we're still doing the -2 to 5 f of x dx minus the integral from -2 to 5 6 dx. So in this one, we know this from the list says it's 18 and then minus whatever the heck we get here. And so to find that, we'll have to take the integral. So 6 turns into 6x, evaluated from -2 to 5. So that's going to be 6 times 5 minus 6 times -2. 30 plus 12, I get 42. 18 minus 42. Ugh. Let's see, what is that? 14, -14? 24. Right? 10, 20 is 22, and then 4 more is 8. All right. Arithmetic is hard. All right. Don't at me. All right, let's see. -2 to 5. This one is worth kind of thinking about a little bit more because there's a little bit more happening. So I'm breaking it up into the two separate integrals again. And it's the same sort of thing, except this one's got a half in here. So what we're going to have to do is pull the half out front. Wait a minute. 1/2 the integral from -2 to 5 h of x dx. That's easy. It's 1/2 times whatever the heck this is, and it tells me it's -11. So it's 1/2 times -11. All right, woo. Then over here with this 5, we're going to have to do the same thing. We'll integrate 5. We'll get 5x, evaluated from -2 to 5. So we'll do 5 times 5 minus, make sure I'm on camera, 5 times -2. So I get 25 plus 10, I get 35. Equals, I don't care. All right. Let's see, G. Now G gets a little more fancy. All right, how would he want us to talk about this? So I think he wants us to just talk about this geometrically. This is, I don't think I've ever done a problem like this before. This is neat. Oh, it doesn't say that. It says from 0 to 7, h of x minus 2 dx. So, the way that we can think about this and not need any new information, because you don't need any new information to solve this. I want to remind you that when we deal with function notation, x minus 2 inside of parentheses moves it 2 to the right. So if you think about this, like if you take x squared minus 2x plus, whoops, no, delete. All right, let's say you take x squared minus 2x plus 1 and you graph it. You have this this function over here. I picked random numbers. I could have done anything, but what if we had done x minus 2 and then x minus 2. So anywhere I saw an x, if I had done an x minus 2 in its place, what would happen to this graph? Well, it takes it and it literally just moves the whole graph to the right 2. So if it moved 2 to the right, does the area change at all? Well, no. And so we can actually think about this as if I were to move it, instead of this, so this is shifted to the right 2. If I move it back, it would just be h of x. If I move it back to the right 2, or back to the left 2. And then if I move each of these bounds to the left 2, well, think about that. Take away 2, go left 2. That brings you down to 5, and this brings you down to negative 2. And now we have something that we know is negative 11. So, pretty tricky, but I hope that was helpful. Now the next one says from negative 4 to 3, g of x plus 2 dx. So this one's moved 2 to the left. And so if we think about this, what if I moved 2 to the left from to get a bound of 3? We'll move back to the right 2, and we get 5. Move back to the right 2, we get negative 2, and that's g of x. Oh, that's when we know it's 5. So then we get I. And I is the first one. Okay, no, D and H, or D and H, wow. G and H, I've never done problems like that before. I liked them, they were neat. I is a classic. We might feel like we don't have enough information for I. It says, what's the integral from 5 to 8 of f of x? And so what we do for I is we set up an equation. We say, oh, hey, I do know the integral from negative 2, am I on camera? Okay, negative 2 to 5 f of x dx. And I also know that if I take negative 2 to 5 f of x dx and I add that to the integral from 5 to 8 f of x dx, what integral is that? And this is where you basically cut out the middlemen and you go the whole way. Almost wrote 8 sideways for some reason. Oh dear. Hey, wait a minute. That's a number we know, right? That's 18. We don't yet know this. And we know that this is 0. Now hold on, that's easy. I can get this by itself, right? Subtract the 18 from both sides. So we can get that integral is just negative 18. So the last few examples are more of the same. They're just a little bit denser. There's a little bit more stuff going on. I really just want to skip them, but they're too good not to skip. So also I'd like to record this one at the top. So let's see, integral from 5 to 8 f of x dx is equal to negative 18, because I might need that later. I also might not need that later, but it's good just to record since I'm kind of losing my papers as I go. All right, let's see. Just a few more. So our next one says take the integral from 8 to 5. So I'm just going to immediately switch that and say 5. No, I want to do a trick with this one, so I'm going to let you know. I'm going to show the complete original. So want to remind you, the trick I'm about to do is, it's like a mid-level algebra trick. So 3 minus 5 is the same as negative 5 minus 3, right? If you don't believe me, well, 3 minus 5 is negative 2. This is regular 2 with a negative out front. So, or you could distribute the negative and get negative 5 plus 3. So, if we ever want to pull a negative out of something, we can reverse the order of the subtraction. Sorry. If there's subtraction in something and you pull a negative out of it, you can just reverse the order of the subtraction. I guess that's basically what I said. But so here, since I see it's from 5 to 8, from 8 to 5, 1 minus f of x dx, I could rewrite this as negative 5 to 8, and still have it as 1 minus f of x, because the integral doesn't change. But then I could distribute the negative in here and get this as the integral from 5 to 8 of f of x minus 1 dx. So for me, it's like, okay, it's just a little bit cleaner to look at. I think it's honestly too much work. It's more work than it's worth, but I've already done it, so too late now. So let's see. So from 5 to 8, f of x minus 1. Okay, so what I could do here is I could say 5 to 8, I actually found that earlier. That was negative 18 minus the integral from 5 to 8 of 1 dx. So now I'll have to say that's x integrated from 5 to 8. So it'll be 8 minus 5. So it'll be 3. So that's negative 18 minus 3. I get negative 21. All right. Our next one and the last one are a little bit of a doozy. So let's make sure that we're careful. So it says in letter K, it says go from 1 to 8 of f of x. Nope, it doesn't say that. F of x minus 3 plus 3 dx. So I'm going to break this apart before I do any of my little moving trick. So this is 1 to 8 f of x minus 3 plus 1 to 8 of 3 dx. So the 3 part we do like we would normally do. We'd say, okay, this is this is 3x going from 1 to 8. So that's 24 minus 3, so 21. And then this one, this is shifted 3 to the right. So if I shift these 3 to the left to get back to f of x, this is 3 to the right. 8 and 1 are 3 to the right. Go 1, 2, 3 to the left. This will be 5. This will be negative 2. And now this is a number we know. So let's see. That's going to be 18 from our known values plus 21. So that's 18 plus 21 is going to be 39. And letter L. So L kind of has the same scenario going on. Oh, you might notice he writes his integral bounds on the top and bottom. I write mine out front. I think that I just learned writing them that way. And in different like math softwares, you can actually put them in either location. As far as I understand, there's no difference. If you ever find out that there's a difference to them, come back and let me know. Even if it's years later, I'd love to know how wrong I am or was. But as far as I understand it, it's just I think it's different parts of the world learn it different ways. Okay, so yeah, we're going to separate this out just like we did the other one. So 2 integral from 2 to 9 f of x minus 4 dx minus the integral from 2 to 9 of 6 dx. I've kind of been doing something without really explaining it. When it's been plus, I've been writing plus, and when it's been minus, instead of saying plus negative 6 inside, I've just been writing minus. The deal with that is I could think about this as a plus a negative 6 if I wanted to, or I could think about it as subtracting 6. And either one is true, and they both work. And since negative 1's a constant, pulling it out doesn't change anything. Okay, so we'll take the antiderivative of this. We get 6x evaluated from 2 to 9. So 6 times 9 is 54. 6 times 2 is 12. 54 minus 12 is 42. This is minus 42. And over here, this is 2 times the integral. Oh, notice how this is moved 4 to the right. So then if I take these and move them 4 back to the left, I'll get 5 and negative 2. F of x dx. And so I can say this is 18. So I get 18 minus 42. I know better than to just try. So is it 24? Is it? No, it's not. It's not. Oh, goodness. Yeah, no, it should be negative 24. These are... I make silly mistakes with these a lot, so just wanted to double check. Didn't want to make us do a mistake. All right. So the last little bit that we're going to do is we're just going to look at some graphs. So evaluate the following by making a sketch of the function. So this says go from negative 3 to 3 and graph x plus 2 dx. So let's see. It's got a y-intercept of 2, up 1 over 1, down 1 over 1. So it's got this graph, and we're going from negative 3 to 3. I could take the integral of this and get x squared over 2 plus 2x and plug in negative 3 and 3 and like do the subtraction and get the number. Or I could go, hey, wait a minute.